in the cold between star systems, where temperatures hover just above absolute zero at -454 degrees Fahrenheit, objects drift for millions of years without purpose or destination. They tumble slowly through the cosmic dark, their surfaces sculpted by radiation and micrometeorite impacts, carrying within their crystalline structure the chemical signatures of worlds that died before Earth was born. These wanderers move according to laws written in the language of gravity and momentum, following paths so predictable that astronomers can calculate their positions centuries into the future with mathematical precision that would make a Swiss clockmaker weep with envy. The space between stars stretches so vast that light itself grows weary crossing these distances. A single cubic meter of interstellar void contains fewer than one atom, making it more empty than the most perfect vacuum humans have ever created in their laboratories. Yet through this near-nothingness, ancient debris from stellar explosions and planetary collisions drifts with the patience of geological ages, each fragment carrying stories written in isotope ratios and crystal matrices formed in the hearts of dying suns. Most of these cosmic wanderers follow trajectories governed by the gentle gravitational influence of nearby star systems, their paths curving in long, lazy arcs that span millions of years. They accelerate toward massive objects, slow as they climb out of gravitational wells, and coast through the empty regions where space-time lies relatively flat and undisturbed. Their motion obeys Newton's laws with the reliability of sunrise, creating orbital equations so elegant that astronomers can predict their behavior with confidence bordering on arrogance. Yet sometimes, very rarely, one of these ancient travelers enters our solar system carrying a secret that makes the equations whisper lies. Its trajectory bends in ways that gravity alone cannot explain, accelerating when it should coast, curving when it should fly straight. The numbers refuse to balance, like a bank statement that insists 2 + 2 = 5. The mathematics sleep fitfully, disturbed by observations that don't fit the comfortable patterns of celestial mechanics that have governed astronomical calculations for 3 centuries. On October 19, 2017, at precisely 7:21 Universal Time, a robotic telescope atop Haleakala volcano in Hawaii captured photons that had traveled 93 million miles from an object smaller than a city block, an object that had been drifting through interstellar space for perhaps tens of millions of years. The Panoramic Survey Telescope and Rapid Response System, known by the acronym PAN-STARRS, collected these ancient photons in its digital sensors, converting starlight into data streams that would flow through fiber optic cables to computers programmed to search for anything unusual moving against the background of supposedly fixed stars. The light carried information encoded in wavelengths and intensity variations, data that would soon challenge everything astronomers thought they understood about visitors from other star systems. The object's brightness flickered with a regular rhythm, suggesting it tumbled end over end as it traveled, its elongated shape alternately presenting its broad side and narrow profile to Earth's patient observers. These brightness variations painted a portrait of something profoundly alien, not in the sense of extraterrestrial intelligence, but in the deeper sense of belonging to a different stellar neighborhood entirely. The Discovery team, led by Robert Warwick at the University of Hawaii's Institute for Astronomy, named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. The name carried gentle poetry, but also prophetic weight that would only become clear in the months that followed. This cosmic messenger had indeed arrived first, the inaugural member of a new category of objects that astronomers would learn to call interstellar visitors, but it delivered questions rather than answers, riddles written in the language of orbital mechanics and hidden accelerations. The object moved with the unhurried patience of geological time, Yet beneath its apparent calm lay mysteries that would keep scientists awake for years, staring at computer screens filled with calculations that refused to resolve into comfortable certainties. Every additional observation seemed to deepen the puzzle rather than solve it, as if the universe had decided to send humanity a cosmic riddle wrapped in the mundane disguise of rock and ice. Initial orbital calculations revealed that Oumuamua approached the solar system from the direction of the constellation Lyra, traveling at a speed that marked it unmistakably as an interstellar interloper. No object born in our solar system could maintain such velocity without the gravitational assistance of planets or the propulsive force of outgassing from a comet's nucleus. Yet, as observations accumulated and orbital models grew more precise, astronomers discovered something that shouldn't have been possible according to everything they thought they knew about how objects move through space. The visitor was accelerating away from the sun, not dramatically, but measurably, consistently, in ways that violated the elegant simplicity of gravitational mechanics. The acceleration was tiny, about a 10,000th of Earth's surface gravity, but persistent enough to accumulate into a trajectory that curved more sharply than pure gravitational dynamics could explain. It was as if some invisible hand gently pushed the object away from our star, applying force so subtle that it barely registered in the most sensitive instruments, yet consistent enough to bend the path of a mountain-sized rock over the course of months. In the darkness beyond Neptune, where sunlight grows thin and the solar wind barely whispers, Oumuamua continues its journey outward, carrying its secrets toward a destination it will never reach in any human lifetime. Its path through space draws an elegant curve that mathematicians cannot quite reproduce with their most sophisticated models, a gentle reminder that the universe still holds surprises for those patient enough to watch and humble enough to admit what they do not understand. The object fades now toward invisibility, its reflected sunlight growing too weak for even the largest telescopes to detect, leaving behind only questions that drift through the scientific literature like cosmic debris, waiting for the next interstellar visitor to arrive and either confirm or contradict the mystery of trajectories that don't add up. The first stranger arrives without fanfare, a dim speck of reflected sunlight sliding across the star-filled darkness like a grain of sand on black velvet. For weeks, this wanderer has been approaching the inner solar system, growing incrementally brighter as it draws nearer to the sun, yet still so faint that only the most sensitive automated telescopes can detect its presence against the cosmic background. Its light carries the chemical fingerprints of minerals forged in stellar furnaces that burned out before our sun ignited. Isotope ratios that speak of planetary formation processes in alien star systems whose names exist only in astronomical catalogs. On that October morning in 2017, when the Pan-STARRS telescope captured the photons that would announce humanity's first confirmed interstellar visitor, the object designated A2017-U1 moved through space with a velocity that immediately marked it as foreign. At over 26 kilometers per second relative to the Sun, it traveled faster than any comet or asteroid born within our solar system could naturally achieve. This speed spoke of origins measured not in astronomical units, but in parsecs, distances so vast that light itself requires years to cross them. The discovery process unfolded with the methodical precision that characterizes modern astronomy. Yet beneath this routine lay a profound moment in human history, the first time our species had definitively identified an object from another star system passing through our cosmic neighborhood. Robert Verick, examining images from the previous night's observations, noticed a point source moving against the background stars at an unusual rate. The object's motion appeared inconsistent with the orbital characteristics of known solar system bodies, suggesting something far more exotic than another piece of asteroidal debris from the Kuiper Belt. Within hours, observatories around the world began tracking this mysterious visitor, their telescopes turning toward coordinates calculated from the initial Hawaiian observations. Each facility added its own photons to the growing database of measurements, building a portrait of an object unlike anything previously catalogued in astronomical surveys. The European Southern Observatory's Very Large Telescope in Chile captured spectra revealing a surface composition reminiscent of metallic asteroids, while observations from the Gemini Observatory suggested unusual rotational characteristics that would soon prove even more puzzling. As the days passed and more observations accumulated, the object's hyperbolic trajectory became increasingly clear. Unlike comets and asteroids bound to our Sun by gravitational chains forged billions of years ago, this visitor followed an open orbit that would carry it past our star and out into interstellar space, never to return. Its path curved around the Sun like a slingshot maneuver executed by cosmic accident, gaining speed as it fell inward through the solar system's gravitational well before being flung back toward the darkness between stars. The International Astronomical Union, faced with humanity's first interstellar visitor, had to invent new nomenclature to properly classify this unprecedented discovery. Traditional comet and asteroid designations proved inadequate for an object that belonged to neither category in the conventional sense. After considerable deliberation, the IAU created a new classification system, designating the visitor as One-Eye Oumuamua, the first object in the I category, reserved for confirmed interstellar interlopers. The Hawaiian name carried layers of meaning that seemed almost prophetic in retrospect, in the native language of the islands where the discovery was made. Oumuamua translates roughly as scout, or messenger from afar arriving first, suggesting both the object's origins in distant space and its role as the harbinger of future interstellar visitors. The name also carried cultural weight, acknowledging the indigenous people whose lands hosted the telescope that made the discovery possible. A gentle reminder that even the most cosmic discoveries remain grounded in terrestrial contexts. Yet, as astronomers celebrated this historic first detection of an interstellar object, subtle anomalies began emerging from their increasingly precise measurements. The visitor's brightness varied in ways that suggested an extremely elongated shape, tumbling end over end as it traveled through space. Its light curve painted a picture of an object perhaps 10 times longer than it was wide, spinning with a period of 7.3 hours that remained remarkably stable throughout the observation period. More troubling still were the tiny discrepancies appearing in trajectory calculations as observational precision improved. The object's path deviated slightly but consistently from the elegant curves predicted by pure gravitational dynamics. These deviations were small, requiring the most sophisticated orbital analysis software to detect, but they accumulated over time into a pattern that couldn't be explained by measurement error or computational limitations. Something was pushing Oumuamua away from the Sun with a force so gentle it barely registered in astronomical instruments, yet persistent enough to alter the object's trajectory in measurable ways. The acceleration was roughly 10,000 times weaker than Earth's surface gravity, comparable to the weight of a paperclip pressing on your palm, but applied consistently over months to an object weighing millions of tons. This tiny force could bend even the most precisely calculated orbital predictions. The mystery deepened as astronomers searched for conventional explanations. Comets routinely experience non-gravitational accelerations as solar heating sublimates volatile compounds from their surfaces, creating jets of gas and dust that act like tiny rocket engines. Yet, Oumuamua showed no visible signs of outgassing, no coma of evaporated material, no tail of dust swept away by the solar wind, no spectroscopic evidence of water vapor or other volatiles escaping from its surface. The visitor appeared to be accelerating without any obvious mechanism to explain the phenomenon, challenging fundamental assumptions about how objects behave in the vacuum of space. As it continued its journey outward past Mars, then Jupiter, growing ever fainter and more difficult to observe. Oumuamua carried with it questions that would puzzle astronomers for years to come. Mysteries encoded in orbital mechanics that refuse to conform to the comfortable predictability of Newtonian physics. In observatories scattered across 6 continents, astronomers bend over computer screens filled with columns of numbers that refuse to behave according to the ancient laws of celestial mechanics. Each measurement carries the precision of atomic clocks and laser interferometry. Coordinates calculated to 15 decimal places. Velocities measured with accuracies that would have seemed magical to Newton himself. Yet beneath this mathematical sophistication lies a growing unease. A sense that the numbers whisper secrets that challenge 3 centuries of gravitational theory. The calculations begin with the fundamental assumption that objects in space move according to gravitational forces and nothing else, unless they happen to be comets actively shedding material into the solar wind. Mass attracts mass with a force proportional to the product of their weights and inversely proportional to the square of the distance between them, a relationship so reliable that space agencies use it to fling robotic explorers across billions of miles with pinpoint accuracy. These equations have guided spacecraft to distant planets, predicted the return of comets with clockwork precision, and revealed the existence of dark matter through subtle gravitational influences on galactic rotation curves. For Oumuamua, however, the mathematics refuse to sleep peacefully. Initial orbital calculations based on the first week of observations suggested a classic hyperbolic trajectory, the path of an unbound object falling toward the Sun from interstellar space before being accelerated back toward the cosmic deep. The curve appeared elegant in its simplicity, a textbook example of gravitational mechanics played out on a solar system scale. Astronomers felt the satisfaction of watching universal principles operate exactly as theory predicted they should. But as observation periods lengthened and measurements accumulated, tiny discrepancies began emerging like cracks in a perfectly smooth surface. The object's position deviated from predicted coordinates by amounts measured in arc-seconds angular distances, so small they would be imperceptible to human eyes even with the aid of powerful telescopes. Yet, for astronomers accustomed to predicting planetary positions decades in advance, these seemingly insignificant deviations represented fundamental challenges to their understanding of how objects move through space. Marco Micheli of the European Space Agency led the team that first quantified these anomalous accelerations, analyzing observations spanning several months to build a comprehensive picture of Oumuamua's trajectory. Using data from telescopes around the world, including NASA's Hubble Space Telescope and the European Southern Observatory's Very Large Telescope, the researchers constructed orbital models with unprecedented precision. What they discovered defied conventional explanation. The object was accelerating away from the Sun at approximately 5 to 10 Drauren 6 meters per second squared, a force so gentle it would take several minutes to accelerate a falling leaf from rest to walking speed. This acceleration might seem trivial by terrestrial standards, but applied to an object weighing millions of tons over the course of months, it accumulates into trajectory changes measured in thousands of kilometers. The effect resembles what astronomers observe in active comets, where sublimating ice creates jets of vapor that act like natural rocket engines, pushing the comet slightly away from its purely gravitational path. Yet, Oumuamua displayed none of the characteristic signs of cometary activity: no visible coma, no dust tail, no spectroscopic evidence of water vapor or other volatiles escaping from its surface. The mystery deepened as researchers considered alternative explanations for the observed acceleration. Solar radiation pressure, the gentle push of photons striking the object's surface, could theoretically account for small, non-gravitational forces. Sunlight carries momentum, and when photons reflect off a surface, they transfer this momentum to the reflecting object, creating a force that grows stronger as the object approaches the Sun. For spacecraft with large solar sails, this radiation pressure provides propulsion for interplanetary missions that unfold over years or decades. Yet, when astronomers calculated the radiation pressure that Oumuamua should experience based on its estimated size and surface properties, the numbers fell short of explaining the observed acceleration by nearly an order of magnitude. The object would need to be far more reflective or much thinner than observations suggested to account for the trajectory deviations through radiation pressure alone. This discrepancy led to increasingly exotic hypotheses about the visitor's composition and structure, proposals that stretched the boundaries of what seemed physically reasonable for a natural object. The Yarkovsky effect, a subtle thermal phenomenon that can alter asteroid orbits over geological timescales, offered another potential explanation. When rotating objects absorb sunlight and re-radiate the energy as infrared heat, they experience tiny propulsive forces as thermal photons carry away momentum in preferred directions. This effect has been measured for near-Earth asteroids, where it causes orbital decay rates measured in meters per year over thousands of years of observation. But again, the magnitude of acceleration observed for Oumuamua exceeded what the Yarkovsky effect could reasonably produce for an object of its presumed size and composition. The thermal forces would need to be enhanced by factors that required increasingly speculative assumptions about the visitor's surface properties, internal structure, or rotation dynamics. Each potential explanation seemed to require its own set of unlikely coincidences or extraordinary physical characteristics. As weeks passed and Oumuamua faded beyond the reach of even the most powerful telescopes, astronomers found themselves confronting an uncomfortable truth. They had insufficient data to definitively explain the object's behavior using conventional physics. The trajectory anomalies were real, measurable, and reproducible across multiple independent analyses, yet no single explanation could account for them without invoking physical properties that bordered on the implausible. The numbers continued their quiet rebellion against gravitational orthodoxy, leaving behind equations that slept fitfully in astronomical databases, waiting for future interstellar visitors to either confirm or contradict the mystery of accelerations that shouldn't exist. Only later would astronomers realize that Oumuamua's strange behavior was not an isolated anomaly, but the first hint of a pattern that would challenge their understanding of how objects from other star systems behave when they wander through our cosmic neighborhood, carrying secrets encoded in trajectories that refuse to follow the ancient rules of celestial mechanics. Through the deep black of interplanetary space, a mountain-sized fragment of some distant world tumbles with the unhurried rhythm of a cosmic metronome, completing one full rotation every 7 hours and 18 minutes. This slow-motion dance has continued for perhaps millions of years, the object spinning end over end as it drifted through the emptiness between stars, its rotational period locked into a stable pattern by the subtle physics of angular momentum conservation. The tumbling motion speaks of ancient violence, perhaps a collision that shattered a parent body eons ago, or gravitational forces that tore material from a planetary surface during a close encounter with another world. As Oumuamua rotates, it presents alternately its broad face and narrow profile to Earth's patient observers, creating a light curve that rises and falls with mathematical regularity. When the object's long axis points toward Earth, its cross-sectional area appears maximized, reflecting more sunlight and appearing brighter in telescopic images. As rotation carries the narrow end into view, the apparent brightness diminishes, sometimes by factors of 10 or more. This dramatic variation in reflected light reveals an object with proportions unlike anything previously discovered in our solar system. The brightness measurements paint a portrait of extreme elongation, suggesting a needle-like form perhaps 400 meters long and only 40 meters wide, proportions that challenge conventional understanding of how natural objects form and survive in space. Most asteroids and comets maintain roughly spherical or potato-shaped profiles, their forms sculpted by gravitational forces that tend to minimize surface area and create relatively compact structures. Yet, Oumuamua appears stretched into a cigar-like configuration that defies easy explanation through known geological processes. Such extreme elongation raises questions about the object's structural integrity and formation history. Natural bodies with aspect ratios exceeding about 3:1 typically prove unstable under their own rotation, with centrifugal forces eventually overcoming the weak gravitational self-attraction that holds small objects together. The fact that Oumuamua has maintained its elongated form despite millions of years of tumbling motion suggests either unusually strong internal cohesion or rotational periods slow enough to avoid disruptive forces. The rotation period itself presents another puzzle wrapped within the broader mystery of the object's behavior. 7 hours and 18 minutes represents a relatively slow spin compared to many asteroids, which often rotate several times per hour due to the cumulative effects of thermal forces and small collisions over geological time. This measured cadence suggests internal structure capable of maintaining coherence against the gentle but persistent forces that tend to spin up small objects through thermally driven torques. Astronomers studying the light curve data notice subtle asymmetries that hint at an irregular surface covered with features that reflect light differently depending on viewing angle. Perhaps ancient impact craters dot the object's elongated form, or compositional variations create patches of higher and lower reflectivity across its tumbling surface. These brightness variations tell stories written in reflected photons, encoding information about surface geology that formed under alien suns in stellar systems whose planets followed different evolutionary paths than those in our cosmic neighborhood. The spectroscopic observations reveal a surface composition reminiscent of metallic asteroids found in the inner regions of our solar system. Yet, with subtle differences that speak of formation processes under different conditions, the reflected light carries the signatures of minerals that crystallized in environments with different temperatures, pressures, and chemical abundances than those that shape the rocky bodies orbiting our Sun. These compositional hints suggest origins in a planetary system where the distribution of elements followed patterns established by a different stellar formation history. As Oumuamua tumbles through space, its elongated form experiences gravitational forces that vary subtly with orientation relative to the Sun and planets. When the long axis aligns with the direction of solar gravity, the object experiences slightly different tidal forces than when it presents its narrow profile. These variations are minuscule by terrestrial standards, but over the course of months, they could theoretically contribute to the tiny accelerations that puzzle astronomers trying to predict the visitor's exact trajectory. The tumbling motion also affects how solar radiation pressure acts on the object's surface. As different faces rotate into and out of direct sunlight, the net force from reflected photons changes direction and magnitude in complex patterns tied to the rotation period. This coupling between spin and radiation pressure creates a three-dimensional dance of forces that complicates efforts to model the object's motion using conventional orbital mechanics software designed for more symmetrical bodies. Temperature variations across the rotating surface add another layer of complexity to the physics governing Oumuamua's behavior. The side facing the Sun heats to temperatures that could sublimate volatile compounds, while the shadowed hemisphere radiates heat into space and cools toward the cosmic background temperature of just a few degrees above absolute zero. This thermal cycling creates expansion and contraction stresses that could fracture surface materials or release trapped gases in patterns synchronized with the rotation period. Yet, despite intensive spectroscopic monitoring throughout the object's passage through the inner solar system, astronomers detected no evidence of outgassing that might explain the mysterious accelerations. No water vapor, carbon dioxide, or other common cometary volatiles appeared in the spectra, leaving researchers to wonder whether the object's composition differs fundamentally from that of solar system comets, or whether some more exotic mechanism drives the observed trajectory deviations. The rotation continues now in the darkness beyond Mars, where sunlight grows weak and the object fades toward invisibility against the stellar background. Each 7-hour cycle carries Oumuamua further from human observation, its tumbling form disappearing into the cosmic deep while still maintaining the precise rotational rhythm that has marked its journey through interstellar space. The spin carries with it all the encoded information about the object's origins, structure, and composition data that will remain forever locked in the mathematics of its light curve, sleeping quietly in astronomical databases until future interstellar visitors arrive to either confirm or contradict the mystery of shapes that shouldn't exist in the orderly realm of gravitational mechanics. Gravity speaks in mathematics so elegant that Einstein called them the most beautiful equations he had ever encountered, relationships between mass, energy, and the curvature of space-time that govern everything from falling apples to orbiting galaxies with unwavering consistency. For 3 centuries, these laws have predicted the motion of celestial objects with such precision that astronomers routinely calculate planetary positions decades in advance, timing eclipses to the second and guiding spacecraft across billions of miles to rendezvous with distant worlds. Yet now, in the quiet halls of observatories around the world, these same equations whisper uncertainties that make even the most confident theorists pause and reconsider their assumptions about how the universe actually works. The deviation appears first as a subtle discrepancy between predicted and observed positions, a difference measured in thousandths of degrees that would escape notice except for the extraordinary precision of modern astrometric measurements. When Marco Micheli and his colleagues at the European Space Agency analyzed months of tracking data for Oumuamua, they discovered that the object's actual trajectory deviates systematically from the path predicted by gravitational dynamics alone. The discrepancy accumulates slowly but persistently, like a clock that gains a few seconds each day until the error becomes impossible to ignore. In the language of orbital mechanics, Oumuamua experiences what astronomers term non-gravitational acceleration, forces that push the object in ways that cannot be explained by the sun's gravitational field or the gravitational influence of planets and moons. The acceleration vector points roughly away from the sun, suggesting some mechanism that operates more strongly when the object lies closer to our star and weakens as it travels toward the outer solar system. This radial pattern resembles the acceleration signatures observed in active comets, where sublimating ice creates jets of vapor that act like natural rocket engines. The magnitude of this mysterious acceleration measures approximately 5 millionths of a meter per second, squared a force so gentle that it would barely register on the most sensitive laboratory instruments, yet persistent enough to bend the trajectory of a million-ton object over the course of months. To put this force in perspective, it equals roughly the weight of a grain of sand pressing against a human hand, but applied continuously to an object the size of a mountain. This tiny push accumulates into trajectory changes measured in thousands of kilometers. Scientists working to understand this anomaly face the uncomfortable reality that none of the conventional explanations prove adequate to account for the observed acceleration. Solar radiation pressure, the gentle push of photons reflecting off the object's surface, could theoretically create forces in the right direction and with the proper dependence on solar distance. Yet when researchers calculate the radiation pressure that Oumuamua should experience based on its estimated size, mass, and surface properties, the predicted force falls short of the observations by factors that require increasingly exotic assumptions about the object's composition and structure. The Yarkovsky effect, which causes rotating objects to experience tiny propulsive forces when they absorb sunlight and re-radiate it as thermal infrared radiation, offers another potential mechanism for non-gravitational acceleration. This thermal rocket effect has been measured for near-Earth asteroids, where it causes orbital decay rates that accumulate over thousands of years into measurable changes in orbital periods. Yet the acceleration experienced by Oumuamua exceeds what the Yarkovsky effect could reasonably produce for an object of its presumed size and rotation rate by margins that stretch physical plausibility. Perhaps most puzzling is the complete absence of any observable outgassing that might explain the acceleration through conventional cometary mechanisms. Despite intensive spectroscopic monitoring throughout the object's passage through the inner solar system, astronomers detect no evidence of water vapor, carbon dioxide, methane, or any of the other volatile compounds that typically sublimate from comet nuclei when heated by solar radiation. The lack of a visible coma or dust tail further confirms that Oumuamua behaves unlike any comet previously studied, yet it experiences accelerations characteristic of active sublimation processes. Some researchers propose that the object might be outgassing materials too faint to detect with current instrumentation, perhaps hydrogen molecules that escape from water-rich subsurface layers without creating visible dust clouds. Hydrogen gas would be essentially invisible to optical telescopes and might escape detection in infrared spectra if the outgassing rates remained below instrumental sensitivity thresholds. This hypothesis requires that Oumuamua contains substantial quantities of water ice despite its asteroid-like surface composition, a combination that challenges conventional understanding of how different types of solar system bodies form and evolve. Alternative explanations venture into increasingly speculative territory, proposing that the object might consist of exotic materials with unusual optical or thermal properties that amplify radiation pressure effects beyond what conventional physics would predict. Some theoretical models suggest that Oumuamua could be a fragment of disrupted planetary material with internal structures that create preferential outgassing along specific axes, or perhaps an aggregation of smaller components held together by weak cohesive forces that allow thermal expansion to create net propulsive effects. The acceleration mystery deepens when researchers attempt to model the object's motion using the same sophisticated software packages that successfully predict the trajectories of comets, asteroids, and interplanetary spacecraft. These programs incorporate decades of accumulated knowledge about gravitational dynamics, radiation pressure, thermal effects, and outgassing phenomena, yet they consistently fail to reproduce Oumuamua's observed behavior without invoking physical parameters that seem implausibly extreme for a natural object. As the visitor continues its journey outward through the solar system, growing fainter with each passing week until it disappears beyond the reach of even the most powerful telescopes, it carries with it a fundamental challenge to humanity's understanding of celestial mechanics. The equations that have guided astronomical calculations for centuries now sleep uneasily, disturbed by observations that suggest the universe still holds surprises for those humble enough to admit that their mathematical models might be incomplete. Gravity continues to whisper its ancient truths about the curvature of space-time and the attraction between masses. But Oumuamua's trajectory speaks of forces that operate beyond the familiar boundaries of gravitational theory. Mysterious accelerations that push objects through space according to rules that scientists have yet to decipher. The discrepancy between prediction and observation lingers in astronomical databases like an unsolved equation, waiting for future interstellar visitors to either confirm or contradict the growing suspicion that objects from other star systems follow different physical laws than those that govern the predictable motions of planets and comets born in our cosmic neighborhood. In the realm of cometary science, where astronomers study the pristine remnants of solar system formation, certain visual signatures mark the transition from inert rock to active sublimating body with unmistakable clarity. When comets approach the Sun and their surfaces warm beyond the threshold, temperatures where frozen volatiles transition directly from solid to gas, they develop the characteristic fuzzy appearance of a coma, a diffuse atmosphere of water vapor. Carbon dioxide, and organic compounds that escapes from the nucleus and expands into space. This outgassing process creates the spectacular tails that stretch millions of kilometers behind comets as they round the Sun, swept away by solar wind and radiation pressure into graceful curves that have inspired human imagination for millennia. Yet, Oumuamua passes through the inner solar system without displaying any of these telltale signs of cometary activity, maintaining the sharp, point-like appearance of an asteroid even as it experiences accelerations that should indicate vigorous outgassing. The most sensitive spectroscopic observations detect no trace of water vapor, carbon monoxide, methane, or ammonia escaping from its surface. Despite the fact that these compounds sublimate readily at temperatures the object surely experiences during its close approach to the Sun. The absence of detectable volatiles presents a profound puzzle for astronomers attempting to explain the mysterious forces that push the visitor away from purely gravitational trajectories. Spectroscopic analysis using the European Southern Observatory's Very Large Telescope and NASA's Hubble Space Telescope reveals surface composition reminiscent of metallic asteroids found in the inner regions of our solar system, with reflectance properties suggesting minerals rich in iron and nickel that formed under high-temperature conditions. These observations paint a picture of an object more similar to the differentiated fragments of ancient planetesimals than to the volatile rich bodies that populate the outer reaches of stellar systems. Yet, metallic surfaces should not produce the non-gravitational accelerations that characterize Oumuamua's trajectory, creating a contradiction between observed composition and observed dynamics that challenges fundamental assumptions about how different types of solar system bodies behave. The rotation period of 7.3 hours, measured through careful analysis of brightness variations as the elongated object tumbles through space, provides additional clues about its internal structure and cohesive strength. This relatively slow spin suggests that Oumuamua possesses sufficient structural integrity to maintain its elongated form despite the centrifugal forces that would tend to tear apart loosely aggregated rubble piles rotating at such rates. The stable rotation implies either unusually strong internal bonding or a monolithic structure carved from a single large body. Yet neither scenario easily explains how such an object could generate the subtle but persistent accelerations that alter its trajectory. Temperature models based on the object's distance from the Sun and estimated thermal properties suggest that surface temperatures during closest approach would have exceeded 300 Kelvin, warm enough to sublimate water ice, and many other common cometary volatiles at rates that should produce easily detectable outgassing. The thermal gradients between the sunlit and shadowed hemispheres of the tumbling object would create expansion and contraction stresses that could fracture surface materials and release trapped gases. Yet no such outgassing signature appears in the observational data despite intensive monitoring throughout the object's passage through the inner solar system. Some researchers propose that Oumuamua might be outgassing hydrogen molecules produced by the radiolysis of subsurface water ice, a process where high-energy cosmic ray particles break apart water molecules and create hydrogen gas that could escape through microscopic fractures in the surface. Hydrogen outgassing would be essentially invisible to optical and infrared telescopes, potentially explaining both the absence of detectable cometary activity and the presence of accelerations that push the object away from the Sun. This hypothesis requires that the visitor contains substantial quantities of buried water ice despite its asteroid-like surface appearance, a compositional profile that challenges conventional understanding of planetary formation processes. The hydrogen outgassing model faces its own theoretical difficulties, particularly in explaining how sufficient quantities of molecular hydrogen could escape from a presumably dense, rocky object without creating other observable effects. The process would require that cosmic ray bombardment over millions of years has gradually converted subsurface water ice into hydrogen gas that migrates through fracture networks to reach the surface. Yet the rates of hydrogen production and escape needed to explain the observed accelerations approach the limits of what seems physically reasonable for an object of Oumuamua's estimated size and composition. Alternative explanations venture into even more speculative territory, proposing that the object might represent a fragment of exotic material with unusual physical properties that amplify radiation pressure effects beyond what conventional physics would predict. Some theoretical models suggest that Oumuamua could be a highly porous aggregate with internal voids that create complex thermal dynamics, or perhaps a remnant of disrupted planetary material with layered structures that respond to solar heating in unexpected ways. The possibility that the visitor consists of materials formed under different stellar conditions than those that shaped objects in our solar system opens fascinating questions about planetary formation processes around other stars. The chemical composition and isotopic ratios locked within Oumuamua's crystalline structure encode information about stellar nucleosynthesis, planetary accretion, and surface evolution processes that operated in an alien stellar environment. Yet these secrets remain hidden beneath the mystery of why the object accelerates without visible outgassing. As weeks pass and Oumuamua fades beyond the sensitivity limits of even the most powerful telescopes, it carries away the answers to questions that have puzzled astronomers since its discovery. The object continues its silent journey through the outer solar system, still accelerating gently away from the Sun according to some mechanism that remains hidden from human understanding. No coma of escaping gases marks its passage. No tail of sublimated materials streams behind it. Yet, something invisible continues to push this ancient wanderer toward the darkness between stars, leaving behind only questions that sleep quietly in astronomical databases, waiting for future interstellar visitors to either confirm or contradict the puzzle of accelerations without observable cause. The silence of Oumuamua's passage speaks as loudly as any cometary display, suggesting that the universe contains types of objects that operate according to physical principles not yet incorporated into humanity's understanding of how matter behaves in the vacuum of space. The absence of expected signatures becomes itself a signature of something fundamentally different about this messenger from another star system. A reminder that the cosmos still holds surprises for those patient enough to observe and humble enough to admit when their theoretical models fail to explain what their instruments detect. In the quiet laboratories where theoretical physicists wrestle with the mysteries of interstellar visitors, a new hypothesis emerges from the intersection of solid-state physics and cosmic ray bombardment, proposing that invisible clouds of hydrogen molecules might explain the enigmatic accelerations that push Oumuamua away from purely gravitational trajectories. This elegant solution draws upon decades of research into how high-energy particles interact with water-rich materials in the vacuum of space, creating a cascade of chemical reactions that could generate the gentle but persistent forces observed in the object's anomalous motion. The theoretical foundation rests on the well-established phenomenon of radiolysis, where cosmic ray protons and alpha particles bombard water ice and break apart the molecular bonds that hold H2O together, creating free hydrogen atoms that can recombine into molecular hydrogen gas. Over millions of years of interstellar travel, this process could gradually convert subsurface water reservoirs into vast quantities of trapped hydrogen that migrate through microscopic fracture networks toward the surface. When solar heating raises surface temperatures above critical thresholds, this accumulated hydrogen escapes into space, creating a nearly invisible form of outgassing that produces accelerations without the dramatic visual signatures associated with conventional cometary activity. Darrell Seligman of Cornell University and Gregory Laughlin of Yale University developed mathematical models that quantify how much hydrogen Oumuamua would need to produce in order to account for the observed accelerations, calculating that the process requires outgassing rates of approximately 10 to the 16th molecules per second, a prodigious quantity that nonetheless remains below the detection limits of current spectroscopic instruments. Hydrogen molecules absorb and emit light at wavelengths that lie outside the sensitive ranges of most astronomical spectrographs, making this form of outgassing essentially invisible to the optical and infrared telescopes that monitored the object throughout its passage through the inner solar system. The hydrogen hypothesis faces immediate scrutiny from astronomers who question whether natural objects can store sufficient quantities of molecular hydrogen to sustain the required outgassing rates over the months-long observation period. Hydrogen represents the lightest and most volatile element in the periodic table, with thermal velocities at room temperature that exceed the escape velocities of small asteroids and comets by large margins. Retaining significant hydrogen reservoirs requires either extremely cold storage temperatures or physical trapping mechanisms that prevent the gas from escaping during the long journey through interstellar space. Theoretical calculations suggest that hydrogen could accumulate within Oumuamua's interior if the object maintained temperatures below approximately 50 Kelvin throughout its interstellar journey, conditions that exist in the deep space environment far from stellar heating sources. The gradual production of hydrogen through cosmic ray radiolysis would create internal gas pressures that could fracture surface materials and create pathways for eventual outgassing when solar heating raises temperatures above the retention threshold. This scenario requires that the object possess sufficient structural integrity to contain pressurized hydrogen while maintaining the elongated shape suggested by its dramatic brightness variations. Alternative versions of the hydrogen hypothesis propose that molecular hydrogen forms through different chemical pathways that might operate more